live here?
Used to.
Who runs this place?
Lady, the name of Mrs. Burke. She's not home.
You waiting for her?
Just came back to get my things. I've been away for a while.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for a show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by Eric Aguilar, who is the CEO and co-founder of Omnitron Sensors.
Greg, Scott, thank you for having me. Really appreciate the time here.
All right, so you have been involved with sensors and sensor integration, firmware, as well as silicon process technologies for some time. Can you briefly just kind of walk through your experience and how that led you to realize a pretty big opportunity?
Yeah, great question. So I actually started my career, I have a technical degree, and I worked at Navy research labs and defense contractors, developing sensors for drone applications really early on. Loved it. I had a great mentor also at the time, which actually helped influence a lot of my decisions and designs. We had a sensor that worked really well with detecting moving objects, but struggled with static objects. And he pointed me to an article in a Nature magazine about something our eyes do. We struggle with the same problem, but we use dithering. In other words, little tiny vibrations in our eyes that allow us to see static objects. Sure enough, we turned on this feature in the sensor and saw a marked improvement in it. So that, like, early on in my career, just got me thinking of like first principle thoughts in terms of how do we approach these problems that we're seeing in the applications that we're developing. And subsequently built a few other sensors, and then some of the technology that we had at the Navy research labs, we decided to license and spin off a silicon semiconductor startup company called Lumidyne. Trent and I, that's where I met my co-founder, my now co-founder, Trent. We had a company that was looking to develop a motion sensor, similar to what you see on your phone here. If you take out your phone and you flip the screen and rotate from landscape to portrait, the motion sensor there is called an accelerometer. That is technology that we developed and brought to the market. It was so great that we got acquired by Google in 2015. Great experience, a lot of fun, really enjoyed it. But I wasn't done. I was still young and really enjoying this field. But I wanted to better understand from like the systems level, what are these sensors really doing at that level, and what are the struggles there? So from there, I went to work for Google X, the Moonshot Factory, and was an avionics lead for a project called Wing, drone delivery. And they're actually in operation today. They're doing operations over in the UK and in Australia and in some small towns here in the US as FAA regulations continue to evolve. But they're doing low-cost delivery, and I came in there really early on and learning how to teach a drone to fly fully autonomously. A lot of fun, really enjoyed that there. And then I got an opportunity to work for Tesla, and that was also a lot of fun. I was responsible for the Model 3 software program, and got that company and that technology from their prototype system to going into production. And I had a team of 300 there at the time. A lot of fun doing that. And again, really going into like, what are the sensors that are going into the system? What are the struggles that I'm seeing here? And then ended up at Argo AI doing, again, sensor integration. And this is when I started seeing the promise of LiDAR, what benefits it could bring to the industry, along with some of its struggles. And that is where, I was starting to see this aspect of there's limitation to what we're seeing going with software. It's frequently thought of that software is going to eat the world, and to some extent that's true. But as good as software currently is, we won't be able to realize the future we imagine with full self-driving without big steps forward in hardware. We saw these fundamental flaws in sensor technologies, and I'm happy to go into some of that. But by going back to first principles was why we founded Omnitron Sensors. And we saw that we have both the experience and the technology and the passion to solve this going back to hardware. And that's where we got into silicon process.
So I think what I'm taking away from what you share in terms of experience is this notion of, always asking the why, right? So, there's quite a bit of precedence in terms of status quo and a big knowledge of body of work and existing implementations. But yet, I think from the early experience that you mentioned through your mentor, it's this notion of, looking at it slightly from a different angle, considering other facets that maybe being overlooked. So I think that really has been something that I see as a continuous narrative that's led to significant improvements to the drone delivery and to the system integration or sensor integration within the Model 3 as well at Tesla. So at Omnitron, what is the big problem that you guys are trying to solve?
Oh, great question. So first of all, I'll start by telling you this, that there's a dozen or so sensors in the phone that we carry in our pocket every day. And seeing that they were just not currently good enough to do the things that we do. And we see this problem firsthand. So for example, when you take out your phone, again, going back to this video example, you rotate the phone left and right, you notice that sometimes the video doesn't turn with you. And this turns out to be not a big issue with us because we can just try again and most likely it works. But when it comes to self-driving, and you need the sensor to work 100% of the time, every time. And this is a term called safety critical, meaning that you cannot have these things fail, or if they're not working, they need to tell you that they're not working. So when I started working at some of these world-leading companies in self-driving, I saw this problem firsthand in a safety critical sensor called LiDAR, or think light radar. For one, LiDAR in its current form lasts only a few months and can fail due to something as basic as the car shaking. So imagine going over a speed bump and losing one of your main sensors. Not ideal. LiDARs are also expensive, costing tens of thousands of dollars each. But the most concerning issue for me was that there was no way of actually knowing that the LiDAR had failed until after the event had occurred. When it comes to something as critical as driverless cars, this becomes a huge, huge problem. So when my co-founder and I were looking at hey, what's going on here? What are the issues that we're dealing with? Both Trent and I have a background in semiconductors, and seeing that this space hasn't seen much innovation in the last 10 plus years, especially when it relates to MEMS, and I can get into that in a minute. We saw that we have a solution that can address this fundamental problem by going, again, back to these first principles and looking well, how do we solve dealing with vibration? Right? When I hit a bump, my eyes don't stop working. When I hit a speed bump or things of that sort, they work just fine. And it turns out that we have a very sophisticated closed loop system around our eyes and our inner ear that compensates for it. To give you a more visual example of this, and for those viewers that are actually watching the video, I put my finger out in front of me. I'm looking at my finger. I move my head up and down, left and right. I'm able to track it independently of what my head is doing. And again, that's that going back to this first principle thinking. It's okay, what's going on there? What can we do there? What can we copy from what nature has already solved to apply it to this industry that has fundamentally been struggling with dealing with issues like hitting a speed bump? And that's when the aha moments hit in terms of doing fundamental innovation down to that level in silicon to bring these new process steps to build these new sensors. And LiDAR is the first market that we're going after to develop this core technology for, but we want to go after the broader sensor space because there's so many other applications that we want to see this used for, as we see fundamental limitations, and really exciting opportunities to build more and more sensing capabilities in the technologies that we use every day.
So let's go a little bit deeper. I think LiDAR is really a system that uses many potential sensors, and within these systems are MEMS, like you're referring to. So if you could help define what that is, but fundamentally, what we're talking about is the way it's currently being developed, right? So
Yeah.
the current approach is something that's called a SMT, or surface mount technology, or also referred to as pick and place. So you have these machines that essentially places the little pieces that makes up the sensors that eventually goes into the LiDAR or other types of systems. And it's that placement that over time, through vibration or movement, starts to lose alignment and starts to have issues around accuracy, or in your case, like you mentioned before, may not even give indication of a failure point, as an example. And all of this kind of attributes to why people like Elon Musk is very much against using LiDAR, is because LiDAR in itself isn't necessarily bad. It just, it's a fail and a cost issue, right? So how are you trying to address this?
Yeah, so it's a great question here. So first, let me tell you what MEMS is. The MEMS are tiny silicon features that are 100 times thinner than a human hair. These are the gears, the levers, the switches at microscopic levels, or think of micro machines that are developing and are used to detect the world around them. This space, as phenomenal as it is, has been relatively flat. The last real fundamental innovation, and what I mean by that, innovation that actually scales to manufacturing and can be produced and is used on an everyday basis, hasn't seen any real innovation, real disruption for 10 plus years. So what Trent and I have kind of coined as a term is we're adding a new degree of freedom to design with. So as nano devices become more complex to accomplish more advanced and sophisticated tasks, having this new degree of freedom to design with at the micron level will become an invaluable part of the process. So some of the key features that we have with our technology, with this process steps, is actually 10x improvement in what is termed as capacitance per unit area. So what that means is better sensitivity at the end of the day. How do I know where this device fundamentally is looking at? The ability to handle the robust or challenging environment of the automotive industry and the robotics industry as well, to handle temperature change, shock and vibration. This becomes a hard part, and I'll get to your point about the surface mount devices in a second as it relates to this. In plane isolation, in other words, having an ability to separate the drive and sense electronics is really challenging to do today, and having that capability is phenomenally better. And then to your point, what I've been seeing with the way these systems are designed, using the surface mount technology has a vulnerability in a couple aspects. One is how accurately you can do this alignment. When you're talking about a laser beam that is millimeters in diameter, that has to travel hundreds of meters, the resultant accuracy that you need to have in your assembly process is at the sub-micron level, or a million times smaller than a meter, or 1,000 times smaller than a millimeter. Like the size of the thickness of a human hair. This is the kind of accuracy that you need to have to put these things together, which is not trivial, number one. And number two, like you said, like holding it there over time has become the endemic problem to these sensors. So you're right, Elon was right. These sensors are expensive and unreliable because of that particular assembly step. So we decided to like throw away the way that's done and look at it again, going back to first principles in how silicon fabrication is done. So what I'm holding up here is a silicon wafer. And you're able to do nanometer level tolerances and design limitations. I mean, we keep hearing about new semiconductor processes that are at nanometer scales. That allows you to do huge amounts of high tolerance features at an inherent scalability of doing thousands of devices at once. So you can build an array of these things right off the bat, make it inherently scalable and preserve those tolerances. On top of that, what you have with going with silicon bonding techniques, you have eutectic bonding or compression bonding, super robust. You're getting away from using epoxy or even solder to hold these things together, which has high temperature fluctuation. And by going to these bonding techniques in terms of wafer-to-wafer bonding, you are building something that's inherently and already automotive qualified for these industries.
So I think the listeners are asking the question, which is, if it's already being done on the semiconductor with chips, the CPUs and GPUs, why isn't it being done on the MEMS side? What's the set of incentive structure and the industry state that it hasn't moved over to that? It seems almost like a no-brainer to use silicon bonding. Why haven't they transitioned to that?
So there are attempts being made there. I think this was part of it is being uniquely positioned to see this opportunity that hasn't been explored before. When you're working on pick and place technology and you're working on those bounding limitations, you're not thinking, hey, look, can I use a silicon process? In fact, they're very, very different skill sets to kind of go at that abstract level. There's also innovation that's needed there. Innovation that we are bringing to this industry with the IP and the process steps that we're developing that have not been done before, and that's I think something that is very unique to what we bring. There's also an inherent high barrier of entry. So if you look at a traditional, even today, right, a new computer chip in your iPhone or things of that sort, these can cost tens of millions of dollars to get into production. So there's a huge level of barrier of entry in terms of just building your one device. So you're not looking at this approach typically, and unless you have like these moments of I think inspiration or gumption to take on these challenges, I think that is generally shied upon to do these type of developments.
So I think you're addressing really the questions I think all of us are going to be asking, which is, so why are you guys better positioned to tackle this when others have been having difficulties because of the high barriers of entry and costs associated? Again, semiconductor foundries are nothing to laugh at. I mean, these are multi-billion-dollar operations. So can you talk about Omnitron ecosystem, how you guys are looking to make this readily available without necessarily having to run foundry from get-go?
Yeah, that's a great question. Again, we are fundamentally looking to become a silicon process company at the broader epicenter of the sensory economy. So we actually work with foundries in the production process. We look to develop it with them. We're partnered right now with a small scale foundry to prove out our fabrication steps, but using them as a way to validate our technology there. And then working and designing and building sensor technologies with other companies as well, and automotive suppliers as our end customers. The model that we want to build will mean that we can reduce much of the inherent risk associated with hardware in terms of capital and time to market. So again, we're stripping off like this dependency on the foundry, this dependency on the end customer, and partnering with them to reduce much of that inherent risk. And this is also actually a proven model that you see with other fabless companies. And a good way to kind of think about this, to kind of abstract and make it simpler, is with similar arrangements that you see with BioNTech and Pfizer in the joint venture to deploy the COVID-19 vaccine. And I also want to kind of bring up to the forefront my co-founder, Trent, who I've been mentioning, but I haven't told you guys about. Him and I, again, met at this company called Lumidai, and we were key leads to bringing this motion sensor to the market, and that led to the acquisition by Google. But Trent, a PhD from Cornell, and is one of the world experts in MEMS. He has over 20 patents and 20 years of experience at the very top of this field, On top of that, he is a renowned scientist at Google, where he runs the quantum computing hardware team that recently achieved quantum supremacy and is considered a watershed moment for computation. But that's the breadth and caliber that we bring to bring this technology to the market. Yes, there are plenty of smart people in foundries that have capabilities, but it's the combination of these models and looking at it from a different perspective that hasn't been done before.
So I want to just kind of briefly explore this business model, this ecosystem that you guys are building out. And the reason this is very important approach is we really don't have a lot of time. And just to kind of put this into context for the listeners is that automakers are literally in public indicating that there is not enough supply of chips and sensors to go into their, regular combustion cars, electric vehicle cars, hydrogen cars, autonomous cars. I mean, they're literally having to slow down their production unit because they can't get enough of chips and sensors. That's the kind of issue that we're having. Not to mention, LiDAR is a big issue to solve. And again, it's not the only one, but it's just got a really high cost. And because of the critical failure aspects of it and the human life and safety aspects of it, being able to address it in a cost-effective manner is very critical. So I guess really the question is, demand is high. The use cases are compelling. How quickly can you guys get to market to meet this demand so that the supply comes up to align with the demand?
Yeah. So great question. There's a few things that we want to do here in the short term, but I also want to talk about our vision in the long term, where Trent and I want to go with this company and go with this vision overall of what we're doing. In the immediate future, by going with this fabless model and with our strong partnership with this foundry, we're able to quickly iterate and design much faster than you can with the traditional OEM, the traditional silicon foundry process. You're typically looking at 18 to 24 months to bring a new sensor, a new silicon product to the market, I should say. We anticipate to cut that down significantly to months. So we'll be able to have our first proof of concept here within the next 3 to 6 months. And that is a phenomenal disruption to how these things are even built and put together. And this brings a significant change to how the industry is going to be able to bring new silicon technologies to the market. To address this bigger issue of having a shortage in semiconductor and you have this geopolitical climate where you have China procuring a lot of semiconductor technology, is we actually want to go back and go to where Silicon Valley started and actually build a foundry. We believe this is an extremely valuable asset to have for ourselves, for our company, being completely biased here, but also as we look to disrupt and bring new technologies to the future, I think you got to go smaller. You got to go nanotechnologies. You got to go and continue to innovate in semiconductors. And I'd say Silicon Valley has lost some of that. And we want to bring it back because we believe that, again, we've reached the limitation of what we can do with software in some of these capacities. And we have to go back to reimagining the future and going and looking at disrupting the semiconductor industry by bringing new technologies that can only be done with teams like ourselves and companies like ourselves that are audacious enough to bring this manufacturing and these foundries that are critical assets for production back.
So just to level set, so everyone's super clear, is that what you're talking about in terms of the fabless foundry is really more longer term aspiration. I think in the shorter term, it's more of a very practical approach to, stripping out the costs, accelerating the speed of design and implementation. But in the long run, what we're talking about is, and I think edge AI chips is a really good example. Is that there's so many new use cases and specific applications that's needed that they're having to develop very tailored microchips, CPUs, GPUs for specific edge cases. And that's an example of the need for really rapid development and deployment and in scale. So that's one. The other thing that you're talking about is whether we're talking about aerospace, which is a hotly contested area, vis-a-vis, state actors like China, Russia, and others. But we're starting to get to a point where, the war of the past that dealt with the tanks and planes isn't really the case anymore. It's communication. It's the laser optics. It's things like satellites that are becoming the new weapons of the future, and all of these things that are super critical to our defense and our ability to protect ourselves as well as our allies really depends on these necessary MEMS, because like you said, MEMS are the ingredients that senses. It's the things that knows the temperature, it knows the frequency, it knows sound, and all of these capabilities around the electromagnetic spectrum. But if we don't have the agility, or if we're dependent upon the supply chain of overseas, just like we've seen with COVID-19 and what it's done in the first several months, where we couldn't even get the basics. What does that do in terms of crippling a nation's ability to protect itself as well as its citizens?
Yeah, that's a great point and a great topic. I think one thing I will add to that is we've seen firsthand, especially in the space and defense industry, the loss of trusted foundries, or foundries that we can do fabrication of highly sensitive technologies. We want to bring that back because we believe that is absolutely essential, not just for us, but also for future development and future innovation. This is extremely, extremely valuable, and a great point that you brought up here in terms of bringing these capabilities back and this innovation here. And it's exciting, and it's exciting for me to be at the epicenter of this and to make this bring this to market, and excited for our future.
Well, we are excited equally that you're working on this with Trent. With that, I've been joined by Eric Aguilar, who is the CEO of Omnitron. Thank you for joining today.
Thank you, Scott.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.